Welcome everybody. Good afternoon to New Zealanders and good day Australia. I guess good morning to the rest of Asia, and good evening to the Americas who have joined us today. My name's Stef Stimson, and I'm RBR's Business Development Manager for Asia Pacific. And although I've only been an employee with RBR since March, I've been their representative in Australia for around 15 years, I think. So I'm fairly new, but I'm also fairly old, as you can tell. I'm hosting this webinar from Australia, and in the spirit of reconciliation, RBR acknowledges the traditional custodians of country throughout Australia and their connections to land, sea, and community. I pay my respects to the elders, past and present, and extend that respect to the Aboriginal and Torres Strait Islander peoples today. RBR have been running webinars for several months now, and it's really great that we've now got a time slot for the Asia Pacific time zones, and it's great because I particularly like it because it means I don't need to get up at 2 o'clock in the morning to participate. All of the other webinars are recorded, including this one today, and you can review it and all of the previous webinars, which have been excellent, via our website. I'm really excited to be able to start the series today with Dr. Hannah Power of the University of Newcastle, which is, for those who don't know, is just north of Sydney in New South Wales. I sold instruments to the University of Newcastle around about 5 years ago, and Hannah's been using them ever since, and she'll be presenting an overview of her extensive coastal work that she's conducted around our beautiful coastline here. The webinar will run on a format of, I'll do a presentation on the technology from RBR that she'll be presenting on, and that'll be about 10 minutes, and then I'll introduce Hannah with an informal brief interview leading to her presentation. There will be time for questions at the end of the presentation, but please feel free to use the chat function in Zoom. My colleagues, certainly Eduardo, you've heard, and Greg correcting me where I've gone wrong with the PowerPoint, so I know they're online, and I believe that my colleagues in RBR China are also online to help as well. So for those who haven't already, if you could turn off your webcams and start and mute your microphones to save some bandwidth. Let's get this underway. So RBR is an international manufacturer of high quality, industry-leading instrumentation. Our focus is high accuracy, low standards, and we have a very healthy obsession with insisting on low power. We break these instrumentation into 4 main groups, being sensors, which the easiest way to think about those are instrumentation which has no internal memory and no internal power, so they're normally attached to something else. Loggers, which are basically a controlling body with power, memory, and processors with sensors attached to it, and they can be used in real time with cables attached to them, or self-contained and left to acquire data while you do something else. We also are involved in building systems, and that's a way of bringing data out into the world, either through modems, communication systems, buoy-based systems like the RBR Cervelo, which I'll show you a picture of in a second, and also external battery packs, so you can extend your measurement program. And we also do a lot of OEM products as well. So the image there is the RBR Argo, which is the standard CTD that is well proven that we produce, and it's been built into a form factor to go onto the Argo floats, the International Argo program. So typically when we talk about this, we show this photo, and you can see the range. And starting from the left, we've got a sensor. That's the optical dissolved oxygen sensor. Moving to a coder, temperature depth logger, multi-channel logger, as going across from left to right, of 5 channels up to 10 channels. and then 2 versions of the CTD, which is conductivity, temperature, and depth, and then the small solo temperature logger at the end. And that's what a lot of people know RBR for, and that's great. However, our family is huge, and even though there's a lot of images on this screen, that's still only a fraction of what we do. So in the hopefully you can see the cursor. In the top left, we've got the Cervelo, which is a communications unit that normally goes into a buoy connected to an inductive modem with a wire walker, which is in the bottom left. The battery packs are between those two, the Fermata and the Fermet, and they're designed to provide external power to extend your measurement programs. At the bottom, we've got the quartz systems, which are high accuracy, low drift pressure sensors based on the Parascientific DigiQuartz sensor. We've got some various OEM sensors in the bottom, in the middle, sorry, the Legato, with our inductive modem coupling, multi-channel loggers, and up in the single channel loggers here. We'll be talking about this Solo D here, which, if you can see my cursor, it's the middle standing up small logger. And we'll go into that in detail. I'll just point out as well, to the top right is an example of the software on one of the platforms we provide software for. So we have PC-based software, or PC and Mac-based computer software, but we also have a mobile version as well to run on Android or iOS phones. So Hannah will be talking today about her work with the RBRsolo D. The D stands for depth, which is a pressure-based sensor. It's a small compact logger, and it's only 210 millimeters long and a diameter of 25 mil. And it's self-contained, which means it's got no external comms on it at all, but it's got internal memory and internal battery. And with all the pressure sensors that we use, it's a Keller pressure sensor. And in the standard yellow form factor, we can extend that to 750 dbar or meters in various ranges depending on the pressure sensor chosen, which is 20, 50, 100, 200, 500, and 750 dbar. We also make a titanium version of the Solo D and all of the other Solo instruments. And they have pressure ranges of 1,000, 2,000, 4,000, 6,000, and even 10,000 dbar in the titanium. Now, the accuracy of the instruments is 0.05% full scale. And it's really important that you choose the best sensor for your range that you're working in, because obviously as the pressure sensor increases, then the accuracy will go with that. But typically a 20-meter pressure sensor will give you an accuracy of plus or minus a centimeter. We've also worked very hard on making these as low powered as possible, and typically at 1 hertz sampling, you'll, on a single AA battery, a lithium thionyl battery, you'll get over a year's worth of sampling with that. And I've shown you some other examples there as well. So it's highly configurable. It's got very fast USB-C connectivity, and as we'll show you on the inside of the instrument in a minute, we can use any battery. The compact depth loggers come in various forms. The D shallow is up to 1,000 meters. You can put the 1,000-meter pressure sensor into a titanium or into this logger. And as standard, it has 2 hertz, up to 2 hertz sampling. It also is available in a 8 hertz, 16 hertz, 32 hertz faster sampling, which I believe is the first, the most recent logger that Uni of Newcastle has bought, is 16 hertz version of that. And we also provide it with tidal averaging software inside it, firmware, and wave analysis and statistical firmware as well inside the logger. The deeper version of it is looks very similar, but it's made out of titanium, has the same type of pressure sensor in the end. And then we also produce add a temperature thermistor to it as well if people are interested in temperature as well as pressure. The Duet TD, which again is available in the same firmwares, and also in titanium as well. So let's have a quick look inside the RBR D. I've got one in my hand there. You can see how small it is. When you open up the instrument, you can see the first thing is it has a couple of O-rings in there for protection to stop water ingress in there. There's a standard O-ring plus a backup O-ring, and then you open up to the inside, and this one here has a Tadiran 3.6 volt lithium thionyl battery in it to give the maximum duration. However, with the Generation 3 loggers, we can actually put any AA battery in there. So for shorter deployments, you may change to a lithium-ion battery you can buy at Bunnings or the hardware store much easier, or for very short deployments, you can even use rechargeable batteries as well. In the middle, and it's quite an apt photo because this one here also is pink, is a dedicated holder for desiccant to keep the moisture out of the logger. As soon as it's that color, you should be replacing it with fresh desiccant, and then on the side there is a USB-C connector, which it's true USB speeds, and you connect to it with the USB-C to USB cable, and you get super fast download speeds. All of this connects to the Ruskin software. RBR has produced a single package of software which is designed to run all the instrumentation. So if you buy a simple Solo or a 10-channel logger, you'll use exactly the same software. So you can set this up to start at a set time or to start and now. By selecting the battery, it will always use the batteries in the instruments, but if you wanted to do some estimation so that you can maximize it, you can choose the battery chemistry, and from that it will change the duration in terms of the sampling speed and frequency, and also the type of chemistry, and then you enable it here, and off you go. If you find that, and we use Ruskin, and please feel free to download the software, it's freely available. We actually use it for marketing, it's very good for planning. And if you find that you'd actually like to get a bit more data out of it, and it doesn't quite work it because you want very fast sampling or very frequent sampling, we have a standard version of it, the Virtuoso and the Duo, which again, the Virtuoso is a D, it's got the same pressure sensor, but it actually has 8 AA batteries instead of the single battery. Instead of 60 million readings, it can sample 240 million. It has twist activation. It's ready to be enabled with Wi-Fi if you need to download it without opening it, and that's particularly useful for profiling instrumentation. And the other advantage is you can have external comms on here, so you can have a connectorized end cap, which has got the desiccant in it as well, and stream serial data through RS-232, 485, USB over the shorter distances. We're going to do, over the next couple of weeks, we're going to do a lot of focus on the D, so we thought we'll bring in a different tip each week. So today's tip, for those who are familiar with Ruskin and may not know about the automatic tasks. So if you're setting up a single logger, it's really easy, intuitive, very simple to do. If you're setting up multiple loggers, so if you've got 9 TDs like our presenter next week is talking about, one of the simple ways to do that is to actually use the automatic tasks. So you can actually set it up as for one of the loggers, and then automatically set it up for deployment by just plugging it in, and it sets up all the loggers. You can also do that for downloading and an auto stopping. So if you're just using 1 or 2 loggers, it's not as useful. But if you can imagine, some of our clients, will buy the Solo temperature logger, and they'll buy those in a batch of 100, and to program each one separately, it's very time consuming, leads to human error, and And so by setting it up to auto download, auto stop, and auto deploy in the various combinations, you can plug it in, it will stop the logger, it will download the data and reprogram it. And so you can whip through your whole batch really simply. Okay, that's as much as I'd like to talk about the technology. I'll just do a quick advert for the future webinars coming up. Next week at the US and North American time zone, Nina Stark from Virginia Tech will be talking about RBRsolo/Ds for measuring pore pressure responses. And then at this time next week, Evan Watterson from Blue Coast Consulting Engineers will be talking about a really interesting project where they used 9 RBR duet TDs on that project. And there's some interesting data for him to share with that. And then the following week, Mara from the Naval Postgraduate School will be presenting on observing beach breaching in California. And Giles, my brother, funny enough, will be presenting on tidal measurements to support hydrographic operations in Queensland from the Port of Brisbane. So there's 4 really nice webinars coming up over the next 2 weeks. So we look forward to welcoming you to them. So that's all for me. There's our contact details at head office and also locally for me here in Australia. And we welcome you to contact us. Now, I will try and do 2 things at once by sharing this and getting Hannah to share her screen. We can unmute you, Hannah. Are you there, Hannah?
I am. Good morning,
Excellent.
Stef.
Well, welcome, Hannah. How are you?
I'm good, thank you. How are you?
Good, thanks. So, Dr. Hannah Power, welcome. Hannah has got over 10 years experience as a coastal scientist and is currently senior lecturer at the School of Environmental and Life Sciences at the University of Newcastle. So welcome, Hannah. It's really nice to have you. Would you tell us a little bit about your background in your area of focus?
Thanks, Steph. So I got into marine science at an undergraduate level, and then I went and did a PhD at the University of Queensland in the Coastal Engineering Research Group up there. And my focus initially in my research was around hydrodynamics in the surf and the swash zone on sandy beaches. And I'm going to talk a little bit about some of the way collaboration with colleagues on today. But I've since kind of expanded my research to include things like tsunami, both earthquake-generated tsunami and submarine landslide-generated tsunami. I've also started doing some research looking at sea level rise and tides in estuaries, and also a little bit of work looking at rocky coasts. And I'm going to also talk a little bit about wave hazards on rocky coastlines today.
Excellent. Oh, that's really good. And you're also heavily involved in lots of organizations. So do you want to just mention your involvement in maybe the Young Coastal Scientists and Engineers Conference?
Yeah, absolutely. I'm really passionate about making our field diverse and inclusive and equitable as it can be. So I'm involved recently I chaired the local organising committee for the first Australian Young Coastal Scientists and Engineers Conference. We were hoping to hold it in person here in Newcastle, but in the end, because of the current global circumstances, we shifted to online. And actually, I think that was a really positive outcome. I can see a lot of names in the participant list here today, and I know that Steph, you people here today. And I'm also a member of the committee of the International Women in Coastal Geoscience and Engineering organisation, where we're trying to increase the percentage of women in our field because we're really in the minority here. So I'm interested in those kind of things. The conference was really about showcasing the next generation of researchers and putting them in the spotlight, and I think we really succeeded in doing that.
Yeah, it's excellent. And the conference was, and I've made this very public in the feedback, but it was exceptionally well organized, run, and the quality of the presentations was really good. So well done. We'll talk a little bit more afterwards. So are you, if before we go into your presentation, there's one thing we always do here at RBR, and we ask you about a single fun fact that you can share with the audience that may surprise them, or maybe even your colleagues don't know about you.
So I was thinking about this and I wasn't really sure what to say, but I think one thing that is something that people might not know about me is that I have commercial scuba diving qualifications. So I have both very high level recreational qualifications. So I'm qualified as a dive master, I can lead dives, but I also have commercial qualifications and have done some quite technical diving.
Excellent, excellent. No, I certainly didn't know that. I knew you were into ocean swimming, but I didn't realize that the diving was there as well. So thank you for that. Okay, well, over to you, Hannah. I think if you can share your screen.
Yep, sure. Okay, hopefully everyone can see my screen now. And I'm just going to move some of the Zoom bits and pieces out of the way. So today I'm going to talk about measuring waves to better quantify coastal hazards. So I'm just going to pick up on a few bits and pieces of research that I've done over the last 3 to 5 years, some of which has been done a compilation of work. And I'm going to talk about a couple of different environments and a couple of different wave hazards that we get. In terms of coastal wave hazards, the two hazards I'm going to be talking about today are wave run-up on sandy beaches. So here we're talking about how far up the beach the waves start to impact. So in this photo, I hope everyone can see my pointer here, this is the limit of wave run-up at this instant, but we can also see really clearly here that, you know, there's been wave impact up to this sort of line where you can see the sand, the sort of footprints in the sand have been washed out. So that's what I'm going to be talking about in terms of sandy beaches. But as I mentioned before, I'm also going to be talking about rock platforms and wave overwash or overtopping on rock platforms. And here we have a view of a rock platform, and you can see that we're getting some wave overwash and wave overtopping on this platform here, just at the edge at this point in time. So I'm going to talk about a bunch of different experiments and some analysis that, as I said, myself and colleagues have done over the years to try to better understand these processes. So kicking off with wave run-up, this is a photo I took back in February of this year. This is Stockton Beach, just on the northern side of the Hunter River here in Newcastle. And you can see that there's fairly extreme wave run-up happening here, and it's starting to impact the dune. So the key research questions I'm going to talk about in terms of some of the work I've done that where we've tried to advance our understanding of wave run-up. What processes drive extreme wave run-up? So what are the key factors that lead to us getting extreme wave run-up? And can we better predict wave run-up? So of course, if we want to understand, for example, whether we're going to get erosion of our sand dunes, whether we're going to get our sand dunes overtopped, we need to understand how big our wave run-up is going to be. So in terms of measuring wave run-up, how do we go about it? This is the photo that I gave to Stef to promote this presentation. And this is a setup from an experiment that we did up on one of the beaches north of Newcastle for one of my PhD students. You can see we've got a chain here running along the beach, and all of these little bright orange flags are pressure sensors. And in this case, we used a number of the RBRsolos, but we also had some other sensors as well. And the kind of data that we get out of a sensor like this looks something like this. And this is a surf zone record, but we have a surface elevation through time. So here we've got 100 seconds, and you can see the blue squares pick out the troughs of the waves, and the red circles pick out the crests of the waves. Now, the other way that we've measured wave run-up here in this setup that you can see is with this LiDAR instrument here, which is a 2D scanning LiDAR. And so each one of these lines that end up looking more like grey shading here represents one beam of the LiDAR. We can see the beach profile shown in black here, and you can see the reflections from the LiDAR off the surface here as the blue dots. So we can see one wave running up the beach here as a bore. If we take these records and stack them up through time. So now we have cross-shore distance shown on the y-axis down here, time on the x-axis, and wave height or water depth in the colours. You can see the individual waves running up the beach, and we can see how far up the beach the waves get. In addition to these kind of measurements, we are also using video data a lot. And so here's an example of a video camera looking over some waves from a beach. I think this photo is actually from back in my PhD days. So this is northern New South Wales. And the kind of imagery we get out of something like that, out of a video camera, might be something like an image like this, which is a Timex image where we've averaged a whole bunch of stills from video. But more often than not, what we're interested in for wave runup is looking at a cross-shore transect. So looking at things in a two-dimensional sense to simplify them, and taking one line of pixels out of every single image in our video, and again, stacking them up in time. So here we now have time across the x-axis, cross-shore distance on the y-axis, and don't worry about the blue line or the red squares or the red dashed lines. All I want to explain here is that what we can see here is one wave coming across the surf zone, hitting the beach, running up the beach, and running back down the beach. So from out of these data, we're able to extract a shoreline, and we're able to extract maximum run-up points. And if our cross-shore transect here in our image coincides with the location of our pressure transducers, we can correlate with depths and extract depth information and combine all these data together. So when we look at a time stack like this, and this is, I've flipped this around, so time is now on the y-axis, time increase is going down, and cross-shore distance on the x-axis. We can pull out, for each individual wave, we can pull out the start of the run-up, which are these green dots, and we can pull out the maximum run-up for each, or the shoreline maxima for each wave, which are these red dots. So now we have a time series of all the shoreline maxima for all the waves in a particular record. So that might be, say, 15 minutes of data from one beach. And what we're able to do with that kind of data is, as I said, we can capture the run-up maxima via the video or the LiDAR. We can correlate that with our pressure transducers and get depths out. We can combine our LiDAR or our video with survey data and convert our cross-shore distances into elevations. So we're then able to see how what the vertical elevation of the run-up is. And from there, we're able to calculate statistical descriptors that describe the wave run-up. So one of the most common ones that's used for coastal management and planning purposes is R2%, and that is defined as the vertical level that is exceeded by 2% of wave run-up events. Now, providing you have a sort of statistically robust sample of wave run-up events, that shouldn't change with the duration of time that you observe for. So if, let's say you observe for 15 minutes or 20 minutes, R2% should be relatively consistently defined. In contrast, our max, or the maximum run-up observed within a given period, will obviously increase the longer you observe for. So in this case, within this 100 seconds, this event here is our maximum run-up, and we can convert this cross-shore distance of, whatever that is, 63 meters or so, into a vertical elevation. But obviously, if we were to observe for longer, the chance of observing a larger run-up maxima is going to increase. And here, when we're talking about run-up, we're relating everything back to the still water depth at the time of observation. So that obviously goes up and down with the tide. So some of the work that we've done has been around looking at what processes drive extreme wave run-up. So as a starting point, we've known for a long time that offshore wave conditions and local conditions really drive extreme run-up. So we all have a sort of intuitive understanding that wave height, wavelength, and wave direction influence wave run-up. The larger the offshore waves, the more likely you are to have increased run-up on a beach. But that has been sort of contradictory to some of the research that we've seen in the literature. So for example, in the early 80s, there was a very strong concept about the saturation in the surf zone, where wave height within the surf zone was purely defined by the local water depth and controlled by the local water depth, which of course would then negate any increase in offshore wave heights, resulting in an increase in wave run-up. We have an understanding that as wavelength increases, wave runup will also increase, and then wave direction relative to the beach affects how much of that wave energy gets into the shoreline. More locally, for a given beach, we have a general understanding that beach slope and morphology affect wave runup. And so, we have an understanding that as beaches steepen, the likelihood of increased wave runup increases. And then the morphology, particularly in the surf zone, so do we have bars and troughs, how steep is the surf zone, those kind of things. While we have an understanding that that has an influence on runup, we don't really have a clear idea of how that factors in and really controls wave runup. So that's a point for future work. But as I said, we need to consider what happens to a wave prior to the runup event. So we need to understand what happens in the surf zone. And so if we think about, our sort of classic model of surf zone, where we have surf zone and swash zone, where we have the runup region or the swash zone, and then we have a surf zone with an outer surf zone and an inner surf zone. What happens in this region here, the outer surf zone and the inner surf zone, is really critical to defining what happens in the runup region. Now, one of the things when we were looking at this that we thought about was, well, what defines the really extreme events? So those runup events that get really far up the beach within your given observation period. And so we asked the question, how do surf zone processes affect wave runup? And one of the really interesting processes that occurs in the surf zone is the process of wave merging, or ball capture, wave overrunning, whatever you want to call it. It's where one wave that is moving faster than the wave in front of it catches up to that wave, overtakes it, and they merge into a single wave. And because they're broken, they're acting like bores. You don't simply have one wave passing over the next. It doesn't keep going and leave the other wave behind. They merge into one new wave. And so what we did was we looked at this process and we tried to quantify it. So here again, we're looking at another time stack where we have cross-shore distance on the y-axis and time on the x-axis. And each one of these colored dotted lines represents a single wave path through the surf zone. And every time one of these paths merge with another path, we're able to identify a ball capture event. And I'll call them ball capture from now on, but as I said, they're referred to by a number of different names in the literature. So every time these two paths intersect, we can define a ball capture event. So and there's a very clear one here where this brown wave is overtaken by this grey wave, and this grey wave continues on. So we looked at how ball capture affects wave runup. And what we see is that it's actually these capture processes that are driving extreme wave runup events. We see that 97% of extreme shoreline maxima are driven by waves that have undergone ball capture. So again, if we look at another time stack, here we've pulled out all the maxima within our time series here. And we've classified them based on whether they're a captured wave. So all the captured waves are shown by the red squares, and all the maxima that result from captured waves are shown by the yellow triangles, and then the maxima that result just from a single wave are shown by the blue circles. And this red and yellow dashed line here represents, the red line represents the mean shoreline position plus 2 standard deviations. So anything above this we can sort of define as an extreme event. And what we found was 97% of the runup maxima, or shoreline maxima, that exceed this cross-shore distance are derived from captured waves. And the other thing that we were able to show is that shoreline maxima driven by capture events extend further up the beach. So when we looked at a whole bunch of data from a whole bunch of different beaches, we see that the average position, so here on the y-axis we've got the swash zone extent, so 0 representing the lowest rundown point. So in this time stack here, that'd be this point here versus the maximum run-up within our given time period. So in this case, that would be here. So we've normalized where all the maxima get to within our swash zone extent, and we can see that the waves that, or the shoreline maxima driven by capture events, which are shown by the yellow bars, in every beach, the mean position of those maxima exceeds the mean position offshore line maxima driven by non-capture events. So this is one thing that we've done that's further allowing us to identify what are the processes that are driving extreme runup. So the second question in terms of understanding wave runup on beaches is, can we better predict wave runup? So if you look in the literature, if you do a search for this kind of stuff, there's a whole bunch of stuff that comes up. So here's a whole lot of equations that we can use to calculate R2%. And again, most of them derive from those parameters I discussed earlier. So most of them have a beach slope in them, so local conditions, and then most of them have something to do with wave height and wave length or wave period. So the bigger the waves get, the longer the waves get, and the steeper the beach in general, we have an understanding that wave runup increases. But in reality, all of these have a lot of disagreement in them. And if we look at how they compare to observations, most of them are subject to large and very variable errors if they're uncalibrated. So here's an example of some work that one of my former students and now colleague, Alex Atkinson, who I believe is here listening today. Hi, Alex, if you're still here. Did as part of a master's project and continued on with in his PhD, looking at, depending on which model you use, so all of these different notations at the bottom on the x-axis represent a different one of these models, most of which are here. He compared observations to data, and we see that the errors are very significant. Remembering that this is a vertical run-up error rather than a horizontal. So here we're talking potentially 2.5 meters in the vertical, which if you're on a 1 in 100 slope is, 250 meters. So we're talking really sizable errors here. And on unseen data, the best performing models can have normalized mean standard errors of up to 0.23, so 23%. So we're talking really significant errors here. So one thing that we can do to improve these is that we can optimize and calibrate the existing predictors based on observational data. So that does require local measured data, so it's not fabulous if you're trying to do something at a site that you aren't able to get out to and collect data from. But it does result consistently in equal or improved performance. So on average, when we do this, our R-squared values increase by about 6%, and we decrease our root mean squared errors or our normalized mean squared errors quite significantly. So we've gone from having, sort of an average error of 23%, our normalized mean squared error of 23, down to 16 here. So we're making significant improvements, but we still have errors. There's also some uncertainty around the value in this. If I go out and I measure runup for 2 days on one beach and calibrate some of these equations to that particular beach, how reliable is that calibrated equation going to be going forwards for different conditions and different beach morphologies? So we can use some machine learning techniques to improve our accuracy of our predictors. So I did some work on this over the last couple of years and came up with this really hideous looking equation, but ultimately is fairly simple to code. It's one line of code, just a whole heap of parentheses, that relies on an understanding of, again, offshore wave conditions, beach slope, and in this formulation we've included a parameter that accounts for the grain size or beach roughness. And when we use this and calibrate it based on data, we can get significant improvements, but you still may require data to test it or calibrate it. But compared to calibrated existing predictors, this still resulted in equal or improved performance. So in terms of understanding wave runup on sandy beaches, there are some considerations and sort of places I think we need to go. So in general, the majority of wave runup observations are from moderate storms or modal conditions. And what we do is we extrapolate those equations and we apply them to extreme storm events. And I think one of the questions that hasn't yet been answered is, can these be extrapolated? What are the errors for these really extreme events when we take these predictors that have been derived from observations from moderate or modal conditions? In general, most work tends to focus on cross-shore processes. And this is a real limitation because we don't consider any alongshore processes or alongshore factors in the development of our predictors or really in our understanding of wave runup. As I said, model predictive skill varies really significantly. Some are better at some sites, some are better at other sites when you test on unseen data. And they also vary within sites. So some are better at high tide on some sites and some are better on low tide at some sites. So there's a lot of variation within those. We can almost always improve them with optimization, but again, as I said, that kind of depends on how much data you have and how much the system changes. And as I said, machine learning can provide some gains. But I do think we need to further understand the processes that are going on in order to be able to improve our run-up predictions. So that's a sort of wave hazards on sandy beaches 101 and some thoughts based on work that I've done previously. So moving on to wave overwash on rock platforms, and I'm just keeping an eye on the time here. This was a project that we did looking at a specific site just south of Sydney in the Royal National Park in New South Wales here in Australia. And the key research questions we wanted to answer here were what conditions drive overwash on rock platforms, and can we predict hazardous conditions? Now, the reason these were our two very specific research questions was this was the site we were particularly interested in. It's a place called the Figure 8 Pools in the Royal National Park. And the site became very famous for this particular pool here that you see in the pink or magenta circle. It became a social media hotspot that went from having a few thousand visitors across an entire summer to potentially a few thousand visitors in a weekend. It was one of those things that tourists would come, they would do the Opera House on Monday, Bondi Beach on Tuesday, and the Figure 8 Pools on Wednesday. But it's a very remote site. It's about an hour hike in, there's no road access. If you were injured at the site, you're required to be helicoptered out if you can't walk out. And so it became a real problem for emergency services and for parks who manage this area. You get a feel for, this is the kind of Instagram shot that people wanted for this, and you get a kind of feel for the conditions here in this photo on the right. It's a roughly horizontal rock platform that sits between about 1 metre to 2.5 metres above the high tide level. So what we did here was we again took the approach of using remote sensing for some of our measurements, and again put in some, here we had to install standalone cameras, so we had solar panels, backup battery packs, and so on. And we tried to sort of minimize the impact on the amenity of the site because it is a national park. And again, we ended up with time stacks. Now these time stacks look quite different because here we have the cross-shore distance relative to the edge of the rock platform. So 0 represents the edge of the rock platform. This is wave breaking over the water, and each one of these white lines represents one wave overwashing onto the rock platform. So you can see that it's relatively sporadic. What we then did was we converted this to a sort of summary plot for a given observation period. So for say a 20-minute observation period. And we used a combination of the pixel lightness, so how bright the pixel was, and then the color temperature of the pixel. Was it sort of a cool color or a warm color? Because the brightness of the rocks caused some problems. And what we ended up with were these, what we called a cross-platform inundation frequency. So the percentage of the time that the platform at this position is inundated. So here at 0, we have the edge of the platform. And in general, we took the blue line using the color temperature to blank out some of these areas where we had anomalous values. So this represents the full width of this time stack. You can see here the edge of the platform at this point where the value drops down really clearly. And then this is this sort of 28 meters or so represents the longest wave of wash event in that particular time stack. Now, obviously, with remote sensing observations, you're not measuring in situ, so we needed to ground truth our data. Here's a sort of alternate view of what an RBR-Solo might look like when you weigh it down with 18 pounds of dive lead and try to make it as innocuous as possible because you're leaving it in the bottom of one of these pools and you don't want someone to nick it. And these sensors were particularly valuable for this deployment because of their long battery life and large memory capacity. So we left them in the bottom of these pools, walked away and went back to get them after a fairly sizable storm event. And they were all still there thanks to all of this lead that we carried into the site. So here's an example of what a record might look like, and this is obviously very mild overwash conditions. Here we've got the depth where we've taken away the mean depth of the pool. So most of these were in sort of pools that were about 2 meters deep. And you can see these little spikes of these overwash events. And when we compare these to the record of lightness, so this is a pixel lightness measure, over the same time period, we can see that all the peaks line up really nicely. So we were really confident that using our in situ measurements, we were confident that our remote sensing measurements were telling us what we needed to know. So here again, we're looking at some of these cross-platform inundation frequency curves for a whole bunch of different times. So as you can see, as we go from the black through to the yellow, the orange, the red, and the purple curves, the distance that the inundation extends over the platform, or the overwash extends over the platform, and the percentage increases, and the percentage of time that the platform is inundated for also increases. And so what we did was we took all of our observations. We had about 8 to 9 months of observations, and for each time period we allocated them into a different category depending on where this curve got to. So did it extend into any of these coloured blocks? And we gave it a category. You know, was there low overwash, minimal overwash, moderate, major, or extreme? So anything that was very frequent or very lengthy in terms of the length of the overwash got classed as extreme, and these boundaries were based on physical features on the rock platform. So this 10 meters is about where the seaward rampart ends. This orange to red boundary is where the figure 8 pool ends. This boundary is sort of represents the more seaward edge of the platform, whereas people tend to sit up in this part of the platform. So these were all based on our observations of the morphology and the usage of the platform. And then from there, we were able to look at a time series. So here we have a hazard category where A is low inundation or overwash and E is extreme. And you can see this is our first month of data that we recorded. For more than half the time, the platform is at extreme overwash. And this is March to April, which is not typically our most energetic time of the year in this part of Australia. And if we compare it to our offshore wave conditions for the same time period, the blue line here represents significant wave height on the left-hand y-axis, and the orange line represents period on the right-hand axis. And you can see that it doesn't take particularly energetic conditions. You know, we're talking significant wave heights under 3 meters to get extreme wave overwash at this site. That line represents the mean significant wave height observed at the location of this wave rider buoy, which was a nearshore wave rider buoy. So you can see that pretty much anything above mean wave height drives extreme overwash. In some cases, longer period events also tend to drive extreme wave overwash. And so what we did was we combined these observations of these hazard categories with our wave rider buoy data and local tides to come up with a way of predicting when we would see hazardous conditions. So we take our forecast tide and wave conditions, we add it to our observations from the site, and we end up with something that looks like a hazard predictor or a risk predictor. So this is the sort of classic model that we use for bushfires in Australia, and I think it's used quite widely around the world. And we sort of took this concept and adapted it to this particular site. So now if you go onto the Figure 8 Pools National Parks website, there's actually a live wave risk forecast tool. And I pulled a screen grab yesterday evening, and you get something that looks like this. You get a risk rating, which you can click on any of these tabs and it gives you information about what the site will be like at that time. And you actually get a 3 to 4 day forecast depending on what time of day it is. So it's 4 days at most, and you get an hour by hour forecast based on forecast tide and wave conditions. So you can see at the time when I was pulling this data yesterday, which was 6 p.m. yesterday, the risk rating was high, and here we see the information for extreme. So to sum up that little bit of work, I think remote sensing offers excellent opportunities to obtain data in really challenging environments. We didn't have anything that we could attach our sensors to without really impacting the natural amenity of the site. But the ground truthing was absolutely necessary to ensure that we were confident that our remote sensing data was giving us what we needed to know. Rock platforms are far more challenging than sandy beaches for both remote sensing and also for ground truthing, because on a sandy beach, you can put in a sand anchor, you can put in a star picket or a waratah if you're in New Zealand, and you can attach sensors. You can, sand tends to look pretty similar across the width of the beach, whereas on rock platforms, you have areas that are wet, you have areas that are dry, and so it's a much more challenging environment to work in. It is possible to forecast wave risks on rock platforms, but site-specific data is really critical, and we found that this site was particularly interesting in terms of how the waves and the tides and the wave direction interacted with the site and the sort of particular orientation of the site and the particular morphology. And I think there are huge challenges in understanding these issues more generally, and this is some work that we really need to work on as a community. There's a lot of work to be done in this space. Just to finish up, I would like to acknowledge all the colleagues and students who have contributed to this work and whose figures and photos I showed in this presentation, particularly those listed there. And then there's a whole host of other people who aren't listed in that list of names who helped out on field experiments, contribute data to these projects, those who provided me with data directly, and there are a few references here from the figures that papers that I've pulled figures from here, but I'm happy to provide references to anyone who is interested. And I'd just like to finish up by thanking Stef for the invitation to kick off the RBR Asia Pacific webinar series. Thank you.
That's excellent, Hannah. Really, really insightful and interesting, and amazing what a wide variety of locations you're working in. So that's fantastic. And you've also come up with a really nice idea for getting. I'm thinking we're going to get some RBR duct tape to. So when people protect their loggers, it doesn't hide the logo. So maybe.
Well, we specifically in that case wanted them hidden because we didn't want people nicking off with them. So.
Yeah, no, absolutely, and a lot of people when they're putting them into areas with a lot of biofouling use duct tape as well, because then it makes it a whole lot easier to clean by peeling off the tape.
Absolutely.
So that's really good. One question we'll open to the floor in a second. But one question I've got for you is that the time frames, particularly on the beaches, you explained it nicely in the pools, but you're leaving your instruments down there for a good period of time to do the observations, and the RBR loggers have got a cost associated with it. The LiDAR system has as well. And you're on some of the most beautiful beaches of the world, so clearly from the images. So how do you minimize the risk of theft?
That's a really good question. We tend to try to, well, as I said with the pools, we wanted to make things as innocuous as possible, partly to minimize theft, but also partly to minimize impacts on a site where people go for the natural amenity and the beauty of the site. You don't want giant, fluoro yellow things all over the shop. On beaches, we tend to work at times that are low patronage for the beaches. So, for example, as nice as it is working in February, January in an Australian summer, it tends to be a time when people are at the beach. There are lots of people around, and so there's I think probably a higher risk of things getting stolen. So we tend to work in winter, or certainly outside of school holidays. That's also about minimizing the impacts that we have on the people who use the beach. We take up a large amount of the beach when we do this kind of work, as you saw from that image. And so we're conscious of the impact that we have, because we're always, when we're working with local communities to use their beach, we're imposing on them and we don't want to make too much of an impact. I found, signs tend to help explaining what you're doing and why you're doing, and then people sort of tend to leave things alone. But for the most part, we've just relied on the fact that people generally don't tend to touch things that they don't know what they are.
Yes, I see. Yes, that's a good. That's quite a nice approach. Doesn't always work in some parts of the world, but it's really
No,
good. That's
touch wood, we've been lucky so far.
excellent. Excellent. Great. I'd like to open the floor to anybody. Does anybody there have a question they'd like to pass to ask Hannah? We're getting some good feedback with a really great talk from Colin, an awesome talk and very informative session. So thank you, Hannah. It's really nice to get that feedback. I think people are
Hi,
either
Hannah, this is Shari and Steph. Thanks for that.
Hi, Shari.
Can you hear me okay?
Yep. Hi, Shari.
Oh, yeah. I just have a question about the bores. Sorry if I missed it. Is that a process that would be more important during storms versus calm conditions, or have you looked at that?
We haven't looked at that explicitly. We see to look at, but it's very challenging getting remote sensing data during storms because for the bore capture work that we were doing, we had an automated algorithm that identified those capture points, and it relied on the color differences between broken and unbroken waves to pull out those wave tracks. And so there are challenges once you start to get water on the lens of your camera and things like that. But look, that's something that we would absolutely be interested in looking at. We didn't see a particularly large difference based on wave height and period alone, but we did see a difference in how much bore capture happened based on the irrebarren number or dimensionless fall velocity. So there is an impact based on beach type. And that's, I think, partly because if you have a much steeper beach, you have a much narrower surf zone. And so the amount of time for one wave to catch up with another is really quite limited.
Well, thank you. I could see it could have big relevance for, planning for storm events and stuff like that.
Absolutely.
Yeah, thanks, Shari. That's a great question. Shari, we've got a couple of questions. Evan, who's presenting next week, so if it's too difficult, you can get your own back next week. No, he'd be interested to know how wave run-up varies with coastal profile, particularly a very eroded profile like Stockton.
Yeah, so in general, the understanding we have is that as beaches steepen, wave run-up increases. There's not really a great understanding in the literature about how the morphology in the surf zone affects wave run-up. So we don't really understand, and I note that Daryl's got a question there about things like single and double bars. We don't really have a very good understanding of how the difference between, say, a single bar or a double bar on a beach affects wave run-up. So that's work that really does still need to be done.
Okay, great. And we've got one here. Have your field measurement data over rocky shore platforms shown any evidence of wave height attenuation when waves traveling across them, comparing to deep water wave height?
Yeah, so we get really significant wave height decay as waves travel across the rock platform. So by the time the waves are up onto that rock platform, they're breaking. And so they are attenuating really quickly. One of the challenges we had with measuring wave attenuation in a sort of cross-platform direction on that site was that we were absolutely limited to putting the sensors in the pools. We couldn't attach them to the rock platform. And so the pools, unfortunately, don't line up in a nice straight line across the rock platform in what you would do in an ideal deployment. So our sort of cross-platform transects tended to zigzag about, and because the platform is curved, we tended to see waves refracting around the platform. It's very clear that wave heights attenuate as they continue to break across the platform, but the rates of attenuation weren't something we were able to look at.
Okay, yeah, interesting. Are there any other pressing questions? Time's pressing on, and I'm wary of taking too much of your time, Hannah.
Yeah, there's one question here from Daryl, which I'm happy to answer, about the ratio of bore captures with beach morphology, which, in short, Daryl, we didn't get to. The only relation we saw was with dimensionless fall velocity and error-barren number. So in a sense, I mean, that is beach morphology, in that, you know, that's sort of the beach morphodynamic spectrum from reflective through to dissipative. So we did see variability with that.
Okay, and you're doing a great job of emceeing as well, Hannah. That's awesome. Did you notice a strong infragravity signal in the sensor camera LiDAR monitoring of the swash?
On the sandy beaches, we do, on some beaches, see a strong infragravity signal, particularly on the flatter beaches, as we would expect. We didn't see that. That doesn't translate into the rock platform work quite so strongly, because it's about whether or not the waves get up over the platform. We tended to see more of a outcome from wave groupiness and wave sets in terms of wave overwash on the platform.
Okay, great. And Colin's asking about cost of instrumentation and you know, how much instrumenting a beach costs. I guess that depends on the type of sensor, how fast you're sampling, whether 2 Hertz will do, or you go all the way with 32 Hertz. And also Colin asks about hiring of these instruments. So there are organizations who have them, and I know from experience, a lot of the universities collaborate together and share instrumentation as well. So there's certainly opportunities there as well. But Colin, you know, we can touch base afterwards, and we can talk about some of the costings directly. So that'll be good. Great. Well, thanks, Hannah. Clearly, with the evidence of climate change and increased storm events, and every time I go to Newcastle, there seems to be an East Coast low hitting there. So with the borders closing, I think it'll be a while before I'm there, so you'll be okay for a bit. But also tie in with the humans' desire to live so close to the coastline and visit the beach. I think your expertise will only ever be in an increasing demand, probably exponentially the way it's going at the moment. So that's good. And also, I wish you luck with promoting women in coastal science and engineering. It's an endless battle. I've done the same as well with the hydrographic side. Very tired of going to seminars and sitting with a bunch of old grey men, and we need to get lots more females involved in all these disciplines, and a lot younger people as well, because there's definitely a void in between. So I wish you luck with that.
Thank you.
Okay, and thanks. I'd just like to thank Hannah again, and thank you everybody for attending. And we look forward to seeing you at a future one. And just remember, next week, Evan Watterson from Blue Coast Consulting Engineers will be here, and we'll see you then. So thank you, everybody. Stay safe and keep well.